Let's turn our attention now to flowing electricity. You'll remember from the last video that conductors are substances with loosely bound electrons in their atoms, which are free to move. If we have a conductor with a negative charge at one end, an excess of electrons, and too few electrons at the other end, the electrons in the conductor will flow, being repelled at the end by like charges, the excess of electrons, and attracted to the other end. Providing the source and sink of electrons are replenished, the current will continue to flow. Many people find these ideas rather abstract. This is because you cannot see an electron in the same way as you can see a normal mechanical object. Because of this, it's useful to have some mechanical analogies which will help us to understand the ideas of electricity. Let's consider water flowing through a pipe as a good analogy to electrons flowing through a wire. First of all, think about the quantity of flow. In a pipe, the flow rate of fluid might be measured as the number of kilograms of water per second, going past a particular point. For example, 2 kilograms of water might flow past a point per second. We say that this is a flow rate of 2 kilograms per second. In electrical terms, this is called a current. We say that 1 amp of current flows when 1 coulomb passes through a point each second. Now you might remember from a previous video that a coulomb of charge is just a large quantity of electrons passing each second. So we get a formula that current I is equal to charge in coulombs C divided by time. 2 amps is 2 coulombs of charge passing a point each second, or if you like, a large quantity of electrons each second. So the current is a measure of the amount of electricity flowing, rather like the flow rate in the pipe. It's just a quantity of electrons passing each second. To measure current, we therefore put a current meter called an ammeter in line with the flow, as shown in the diagram. What then is voltage? Let's go back to our pipe analogy to see. Why does water pass through the pipe in the first place? It does so because there is a difference in pressure at each end of the pipe. The pressure creates a force which pushes the water through. In fact, pressure is equal to force over area in a pipe. This might be created by a pump, or because one end of the pipe is higher than the other. In the electrical system, the difference in amount of electrons at the ends of the wire are what causes the current to flow, because they generate an attractive or a repellent force. This is voltage. Voltage is the pressure which causes current to flow. There can be no current without a voltage. In the pipe, we can measure the pressure either by comparing it at the ends to some standard, which is usually just ambient air pressure, or alternatively by measuring the difference between the two ends. Similarly, with voltage in a wire, we can measure it at each end and compare it to the voltage of the ground outside, for example with a metal rod sticking into it. This ground reference is called earth or ground or 0 volts. Alternatively, we could also measure the voltage between the ends, and this is very commonly done. This is called voltage difference. Either way, a voltmeter is used across a circuit, not in line with it like the ammeter. Look at the diagram below, which shows a bulb, and this will illustrate the point. However, one difference between voltage and current is that it is possible to have a voltage without a current, in the same way as you can have a pressure without flow. Think of sticking your finger across a hose pipe. The pressure is still there, pushing on your finger, but there's no flow of water. In an electrical sense, this is like the static electricity which we saw in the previous video. There is a pressure, the voltage caused by the excess of charge, but it's not flowing because it hasn't got a conductor to flow through. And even if it did, it would just flow very quickly away because the electrons are not being replenished by anything at the other end. Because of this, voltage is sometimes called potential, because it's like potential energy. It has a potential to make current flow, but it doesn't necessarily have to make a current flow. As current flows, it doesn't have it all its own way. Atoms get in the way, electrons are attracted to each other, or they can be scattered by impurities within the conductor, or disrupted by the temperature of the conductor. Therefore, flows have a resistance. Such scattering causes a material to heat up. Without resistance, even the tiniest voltage would cause a huge current to flow. Different materials have different resistances by virtue of their different atomic structures. Resistance is related to voltage and current by Ohm's law, R equals V over I. In other words, resistance is a ratio of voltage to current in a circuit. A resistance of 50 ohms means that for each amp to flow, 50 volts are required. So if we see a circuit with 50 ohms resistance, we know that the voltage will be 50 times higher within that circuit. Finally then, what about energy? Because current is a flow of electrons, these carry energy with them, as does anything which is moving. The formula for the energy of a flow is that energy is equal to ITV, where I is a current, T is a time, and V is a voltage. However, it's usually easier to measure the amount of energy per second passing a particular point, and this is called power in watts, which is equal to IV. In other words, power is equal to energy divided by time. You can show quite easily for yourself that this is also equal to V squared over R, or I squared R in a circuit which has resistance. Power is just a measure of the oomph of the electricity which is passing through a particular point and takes into account both its current and its voltage. In other words, both the quantity of electricity passing and the pressure behind it.